Welcome to Study Loop.
Hello there, this is Josh. We are interested in the range of the force mediated by this omega particle. All right. So for starters, a good way to approach this problem is to approach it the same exact way that our textbook does, the way Yukawa evaluated what energy, or rest mass rather, hit the particle mediating nuclear forces would be. This starts with the uncertainty principle in this form. Delta E delta T is greater than or equal to h bar over 2, where h bar is equal to Planck's constant divided by 2 pi. Okay, so to start with, first let's estimate the time it would take to mediate this force. So we're going to rearrange this equation and solve for delta T. So delta T is equal to h bar over 2 delta E. This will be the first equation we're going to use. Now, in Yukawa's estimated time scale, he estimated that the time of interaction is likely going to be related to the length scale divided by 2 times the speed of light, which is the upper limit for speed for these interactions. Now, this will be our second equation. If I set 1 and 2 equal to each other, I can get an expression for R naught involving just h bar and energy. Let's do that. Setting 1 equal to 2. H bar over 2 delta E equals R naught divided by 2C. All right, immediately we see that the 2's are going to cancel. So let's simplify. H bar over delta E equals R naught divided by C, and simply we'll multiply C over. So now I have H bar C divided by delta E equals R naught. And that is going to be the range of this. Now if we plug everything in here, I'm going to break H bar into its components. HC divided by 2 pi delta E. Now in previous videos I've talked about this. This value HC, it's useful. This is really handy on a test. Is 1240 eV nanometers divided by 2 pi times the energy given in the problem for this particular particle, which is 783 MeV per c squared, rest energy. And the energy of that particle is its mass times c squared equals m c squared. C's cancel. Okay. When I do this, what I get is that this is equal to 2.5 times 10 to the minus 16 meters. Or if you leave it in nanometers, this is equal to 2.5 times 10 to the minus 7 nanometers. But that is an odd unit. Generally, you want it right, a power like this with a prefix. So we will leave it in this form. Very well.